So let's talk about making a graph when you finally collect your data. So what's the first step in making a graph? Title. Who said it? Noise. Title. What's a good title for this graph?
And guys, I am recording this for absent people, so let's do a good job.
Is that
Time to
sorry, who said it? Time versus average length, maybe? What are we missing? Does this tell me what we're measuring or what time actually means? What if it means like time a day? What am I missing here? How can I fix this? What's up?
minutes.
Okay, time in minutes. Time in minutes. Okay. What else?
Yeah, millimeters of average.
We do need units here, so millimeters. Right. What am I actually measuring though? Of what?
Nothing.
That one you would get nothing if you measured it. What are we measuring?
Dependent variables on
The potato, right? And what are we measuring in terms of time, right? It's time in the salt solution. So I want time in 25% salt solution versus average potato length, right? You want as many details as possible because when someone looks at your graph, they want to know exactly what they're looking at. Why is that important? Why do we even care? Why do we care about graphs? Come on, McKenna. Why do we care? Why am I making you do this?
Because it's an assignment.
Nope. Nope.
So you know how to graph?
So you know how to graph. When you do an experiment, what's the point?
To show the data.
To show the data. If I just give you a bunch of data, right, a bunch of numbers, is that really helpful to you? Not really. This is so you can see what's actually going on with your data. When I go to read like journals and stuff, I don't look at the numbers, I look at the illustrations. I look at the graphs, right? Because that's where I can get all the information that I need. Okay. So in your title, it should reflect that. What's next? X and Y axis things. Okay. How do I decide which one's which?
Which one's the independent variable?
Where's the independent go?
The bottom.
The bottom. So your independent variable should always be on the bottom. What's our independent variable?
Time.
Time. In minutes. Okay. Which means average length goes on this side, and it's in millimeters. Nice. So when we figure out the scale that we want for our axes, you got. Why is it important that I don't just put everything in the little corner here and call it a day? Why can't I just graph it here and then I'm good? Yeah. Good. Why? Yeah, I mean, it's empty, it doesn't look as nice, but you also want it to be as big as possible because it is easier for me to read if I do take up all that space. So what I would do is over here, start at the time that you begin. I believe I figured it out, and it's every 4. So every 4, you should put another 10, so 20, 4, 30, 70. Yep, and we want to go all the way to 70. 60, 70. Okay, so we used all our x-axis. I believe we're going to do every 2 here, so it's every 0.5. I made that mistake last time. 1.5, 2, 5, 3.
And you guys can pull your labeling over to the side so it doesn't appear.
Yeah. I make that mistake every time. Okay, so we have our axes labeled, we have our scale set, we have a title. What do we do next? We got to graph it. How do I know what type of graph to make? I saw some people put bar graphs on. Is that the right graph to make?
No.
No. Why? Anybody?
Because the data.
Because of the data. Really, it's because of your variables. How am I measuring my variables here? I've got time, which I can break up into smaller increments, and I've got average length, which can also be broken up. Bar graphs are great, but only when you have what we call categorical variables. If I was measuring something like, I don't know, if I was looking at water loss with a type of potato, maybe a bar graph. But here I have, what's that?
Cars.
Cars, right, cars. Here I've got what we would call continuous, because time can keep going on and on and on. And I can make it much smaller, right? If I wanted to do 5, I can make it 5. Same thing here. It's continuous. So the best graph to do would be a line graph. Does that make sense? Okay. So now that I know what type of graph I'm doing and I have all my axes set up, I can go to my data. So data's up there, but our first point at 0, the potato that didn't go into the solution, was up here at 5, right? And then I would just go down every one. So my potato that I took out at 10 minutes, it was over here at 4.5. Right? And what you should end up getting, it won't be exactly like this, but it should be something like this. Oops, sorry, fixed. So I believe at the 50 is when we kind of taper off. So it should look something like that. It won't be exact. So what can I actually tell? What should my conclusion be looking at the data? Take your time if you're graphing it now. But those of you who did it right, what can I tell from this?
My conclusion is that the longer the potato cube stayed in the solution, the shorter its average length was.
Or water loss. The longer it's in the salt solution, the more water is lost. But what's happening here? Why does it taper? It stops. Right. So here it's reached what we would call an equilibrium. So we're going to talk about that when we get to osmosis. But basically, it's losing, and then it doesn't lose anymore. It stays consistent through time. So if I wrote revised graph on the back, or if you didn't do it, here it is. I'd write it down and do it. Does anyone have any questions about graphing? Sorry. Makes sense, right?
Guys, take a second, double check. We're going to erase in a second, and we're going to stop recording. I'd like to hear Brandon with Flint. We'll work on the name.